Swarm robotics, coordination and control mechanisms. Introduction. The essence of swarm robotics. Coordination mechanisms. Control mechanisms. Challenges and future directions. Conclusion. The essence of swarm robotics. Inspiration from nature. Swarm robotics takes its cues from natural systems where simple rules governing individual behaviors lead to emergent, complex group dynamics. For instance, ants can find the shortest path to a food source without any central control by laying down pheromones that guide other ants. Similarly, birds in a flock maintain formation by adjusting their position relative to their neighbors. These natural examples demonstrate how local interactions can lead to global patterns and functionalities. Applications of swarm robotics. Swarm robotics holds promise for a wide range of applications. In agriculture, swarms of robots can be used for tasks such as planting, weeding, and harvesting. In disaster response, robotic swarms can search for survivors and assess damage in hazardous environments. Other applications include environmental monitoring, surveillance, and space exploration. The scalability and robustness of swarm systems make them suitable for tasks that are challenging for single, monolithic robots. Coordination mechanisms. Local interaction rules. The foundation of swarm robotics lies in simple local interaction rules. Each robot in the swarm follows a set of basic rules based on its local environment and interactions with nearby robots. These rules can govern various behaviors, such as movement, communication, and task allocation. For example, a rule might state that a robot should move towards a target if it detects a signal within a certain range, or avoid obstacles and other robots to prevent collisions. Stigmergy. Stigmergy is a mechanism of indirect coordination through the environment. It is commonly observed in social insects, where individual actions leave marks or signals in the environment that influence the behavior of other individuals. In swarm robotics, stigmergy can be implemented using digital pheromones or virtual markers. For instance, robots can drop virtual markers in a shared environment to indicate explored areas or potential hazards, guiding other robots to or away from these markers. Consensus algorithms. Consensus algorithms are critical for ensuring that all robots in the swarm agree on certain variables or states, despite possible differences in initial conditions or local observations. These algorithms enable coordinated actions such as forming a specific shape, maintaining a formation, or synchronizing movements. Examples include the leader election algorithm, where one robot is chosen to lead a task, and the average consensus algorithm, where robots iteratively adjust their states to reach a common value. Control mechanisms. Decentralized control. Decentralized control is a hallmark of swarm robotics, where there is no central authority dictating the actions of each robot. Instead, control is distributed across the swarm, with each robot making decisions based on local information and peer interactions. This approach enhances the robustness of the system as it eliminates single points of failure and allows the swarm to adapt to changes in the environment or the loss of individual robots. Behavior-based control. Behavior-based control involves designing robots with a repertoire of behaviors that can be triggered by specific environmental cues or internal states. Each behavior corresponds to a simple action or series of actions, such as moving towards a light source, avoiding obstacles, or following a gradient. Robots switch between these behaviors based on predefined conditions or rules, allowing them to respond adaptively to their surroundings. Artificial potential fields. Artificial potential fields are a technique used to control the movement of robots by generating attractive and repulsive forces within the environment. Each robot experiences these forces, which guide its movement towards goals, attractive forces, and away from obstacles or other robots, repulsive forces. By adjusting the strength and influence of these forces, robots can achieve coordinated behaviors such as flocking, dispersion, or aggregation. Challenges and future directions. Scalability. One of the significant challenges in swarm robotics is scalability. As the number of robots in a swarm increases, the complexity of managing interactions and ensuring effective coordination also rises. Research is ongoing to develop algorithms and control mechanisms that can scale efficiently with the size of the swarm, ensuring consistent performance regardless of the number of robots. Robustness. Robustness is crucial for swarm robotics, especially in dynamic and unpredictable environments. Ensuring that the swarm can continue to function effectively despite failures or malfunctions of individual robots is a key area of focus. Techniques such as redundancy, fault tolerance, and adaptive behaviors are being explored to enhance the resilience of robotic swarms. Communication. Effective communication is vital for coordination in swarm robotics. However, communication bandwidth and range can be limited, especially in large-scale swarms. Developing efficient communication protocols that minimize bandwidth usage and can operate under constrained conditions is an ongoing area of research. Solutions such as implicit communication through environmental cues, stigmergy, and minimalistic direct communication are being investigated. Ethical and social implications. As swarm robotics technology advances, it is essential to consider its ethical and social implications. Issues such as privacy, security, and the potential for misuse in surveillance or military applications need to be addressed. Additionally, the impact of deploying robotic swarms in various industries on employment and social structures must be considered. Conclusion. Swarm robotics represents a paradigm shift in the field of robotics, leveraging simple, decentralized strategies to achieve complex, coordinated behaviors. Inspired by nature, these systems hold immense potential for a variety of applications, from agriculture to disaster response. The coordination and control mechanisms that underpin swarm robotics, such as local interaction rules, stigmergy, and decentralized control, are critical to their success. Despite the challenges ahead, continued research and development in this field promise to unlock new capabilities and opportunities, making swarm robotics a fascinating and impactful area of study. Thanks for watching. Subscribe us.